Alright, so happy snow day. I am so considerate that I'm going to give you a lecture today on chapter 11 so that we can stay on schedule and that we don't really lose a day. The first thing that I want to just give you a hint of, and I will talk more about this in class tomorrow, is that I wanted to finally introduce you to your assignment for a scientific paper presentation. You probably saw in the syllabus that this is one of the things you'll be graded on, and so we're going to start talking about deadlines and getting moving on that assignment. Basically, I want you to find a simple paper that's related to mechanics. It doesn't have to be statics. It could be either statics or dynamics. Hopefully something that applies to some of the concepts that we have either covered in class or that you see that we're going to cover. And basically, in your presentation, you'll be presenting the class, to the class, your paper, helping them understand what the whole point of the paper was, and also being able to fill in the blanks of what might not have been in the paper. And so that's where I want you to sort of use your mechanics skills to do that. I do want it to be a relatively simple paper. Things can get pretty hairy pretty quickly. And so I'm recommending that you look at something like the physics teacher or something like the American Journal of Physics. Just a spoiler alert, Dr. Ashman actually has a short paper published in the March issue of the physics teacher, so maybe someone will get to do that. So you're probably wondering when you have to worry about this. I want you to start looking for a paper, and I want you to submit a PDF of that paper by March 20th. There's already an assignment in Sakai that you can do that, so you're always welcome to do it earlier. Please submit the PDF and not a link, because depending on where I look at the link, I can't always access it, so that just wastes a lot of time. If I feel that the paper is appropriate, then we just move on. Otherwise, I might ask you to circle back and look for something better. And when I'm doing that, I'm just trying to keep you from suffering too much. I'm going to also ask you to have a rough draft of the presentation turned in by April 6th. That would be some PowerPoint slides so that I sort of see that you're making progress. The presentations then we'll schedule on the last days of class. And we don't have to worry about that too much. But those are your two major deadlines that you have to think about for right now. All right, so we're going to look at chapter 11 today, and basically what I'm going to concentrate on in this lecture is the idea of virtual work. And so basically what we're doing in chapter 11 is it is another way, particularly with the idea of virtual work, to get the relationships between different forces in a different way. Instead of using the equilibrium equations, we're going to sort of use this idea of virtual work, so which can be confusing. When I'm talking about the forces that you're going to be finding, the forces would include the forces of reaction. Remember, like the forces that a pin is exerting on a beam, or the force, the moment reaction that it has of a beam embedded in a wall, things like that. So we've been finding these a lot in using the equilibrium expressions. Basically, we're also going to think about, and this is something we'll do on Wednesday, if you sort of use that idea of virtual work and apply it to the potential energy function. If you remember, work and potential energy are inversely related in a way. Like when you do work, when work is done on a system by a particular force, the potential energy associated with that force will decrease. In any case, using this idea of virtual work, we'll also be able to figure out if an equilibrium that we're looking at is stable or unstable. Like I said, that'll be more for Wednesday. So, first of all, we want to just review what we mean by work. And I also want to have you notice that the the notation that we're using might be a little bit different from what you're used to, because we use the term U for work, and I think that probably in general physics we used U for potential energy. So I always find that sometimes those changes of notation can throw me, but hopefully you're not so easily thrown. So just notice that if we have a force applied to an object, we have the force applied right up here. If there is any sort of displacement of that object, notice that this object has moved in this direction, then we know that there's work done. Work is given by the scalar or dot product. And remember that the scalar or dot product, the one name of it comes from the fact that your result is a scalar quantity. And the other thing is, how do we calculate the scalar product? So if we say du is f dot dr, remember that we can write that as the magnitude of the two vectors, f and dr, and then times the cosine of the angle between them. One way to look at that, if we look at this picture right here, this quantity right here is the component of the force that is parallel to the displacement. Of course, this component we might call F perpendicular wouldn't contribute at all to the displacement, and so that's one way that we can think of it, that definition, and why it makes sense. So that's one way that we can think of how to write work. So we also want to know how work can be done if we have a couple. Remember, a couple is a force, equal and opposite forces that are displaced by a distance. Here the distance is h. And if we were trying to find the moment due to those two, or not find the moment, find the work done by those forces, one of the things that we want to remember is this is helpful, because when we're talking about moments or couples, we remember that there's a relationship between, say, the arc length and the radius and the angle. That'll be theta. And the way that they're all related is S equals R theta. And so what that is doing for us is that allows us to remember that if we have some sort of displacement in an angle, how we could write sort of a linear displacement in the same direction. So if we go to this picture right here, notice that we're showing that these two forces that are acting as a couple have resulted in a displacement that is most easily described by the displacement in the angle, d alpha, and each one of those forces. Now, how would we talk about the distance? And that would be this distance right here. Well, that could be written using this information here as h over 2 times d alpha, and then we have two of those forces, because there's one on each side, would give me the total amount of work done by that couple. And because the 2 factors out, I have F times H times d alpha. And here you might remember this would be sort of how we would define the couple due to those two forces, and we'll write that as M times d alpha. So I feel like the point of this is showing how we might calculate the work done when there's some sort of rotation. We can write it as a force times a distance if we use this relationship to figure out how to write the distance, or we can also write it as the moment times the difference in the angle. There was a question. Someone said, what do they mean by sense? Because I know that in the book they talked about the sense of the couple, the M and the alpha. And basically what they're saying when they say sense is like, which way would it cause a rotation? And so they're saying that if the couple and the d alpha both would be talking about rotation in the same direction, then they would both be positive. If one is talking about a rotation in a different direction than the other, then you're going to have some sort of negative sign because you need to account for that difference. Oops. All right. So the whole point of virtual work, like what are we doing, is we're talking about some sort of virtual translation or rotation. And so the idea is that we're looking at our structure, and instead of just writing the equations of equilibrium, we're going to imagine what would happen if this beam or series of members were displaced in a particular way, in a very small displacement. What kind of work would be done by the forces acting on the beam in that sort of imaginary translation or rotation? And so the idea being that if everything is in equilibrium, no work is going to be done. And so again, sort of the question came up is, why do we do this? And the bottom line is, if it is in equilibrium, remember, if it's in equilibrium, it means the sum of the forces add up to be zero. But that would also then necessitate that if the object underwent some sort of displacement, the forces that would do work in that situation the work that they do should cancel out as well. And so what it does is it sort of gives us a new way to come up with the relationship between all our forces by looking at the virtual work instead of just using equations of equilibrium. So, here is an example where we might be using virtual work. And so the first thing that is done is the free body diagram, where all the forces are identified and labeled. And now we're going to look and imagine for particular displacements. And so, someone said, why do we assume the displacement? It's really just sort of the nature of this technique, is that we're really using the idea that if the object's in equilibrium, no work could be done on it because the forces would cancel out. And so it gives us another way to get at the relationship between the forces. So what we're going to do is, here's our object, and we're going to imagine it being displaced in particular directions. We're going to do 3 different displacements, and that should give us 3 different expressions that relate our values. So we're going to imagine in the x direction, we have a displacement, a virtual displacement of delta x, and we see that right here. And so we want to think about, of all these forces and moments acting on the object, which ones would do work? Well, obviously, the vertical forces aren't going to do any work in this situation, and neither will the moment. So the only forces that'll do work, and so we're going to just start writing down, AX would do a positive amount of work, and it would be equal to the force times that displacement. That normal force, the force that the wall was exerting on the beam, that force is in the opposite direction or sense of the displacement, and so that's a negative amount of work. And so we come up with this expression based on our idea of virtual work, that the total work done is 0. We notice that we can factor out the displacement, and because this isn't 0, it requires then that the quantity in the parentheses must be the quantity that is 0. And that gives us one equation that shows us the relationship between the two quantities. Now we're going to do a displacement in the y direction. And so again, we'll write the work done. This time AY would give a positive amount of work. The weight would give a negative amount of work. And so we're going to factor out the delta Y. And again, we find the relationship between the two quantities. Okay? And then finally, we're going to imagine for our virtual displacement be a virtual rotation. And so we have to think about which forces might act if I have this rotation. Notice how it was written, the displacement. And so it kind of, we went from this location up to here. And all right, so we're going to imagine the displacement. And so we have delta U. Now for the moment, we have m times delta alpha. And then we also have the work. Now, for the work, it does do some it is gonna, I'm sorry, not the work, the weight. The weight is gonna do some work, but we have to think about this more in terms of the force times the linear distance that it would move. And the linear distance that this object moved right here is the 1/2 L, because the weight is placed at the middle of the beam, times delta alpha. But we want to think about the component of work that right here, which is perpendicular to the rod itself, because the other component, which is parallel to it, wouldn't do any work as it was moving in that direction. So we have W cosine of alpha times L/2 times delta alpha. So that's for that. And then finally, we have minus, now for the normal force, we actually only want to look at this component, which is in that direction, and that's N sine alpha times L. And all this is work that is equal to 0. Again, we're going to factor out the delta alpha and get M plus W cosine alpha times L/2 minus N L sine of alpha. And so that one was a little bit harder, but we still are going to get a relationship between our values. And so you can see that what we did here is with these 3 different virtual displacements, we can sort of come up with these equations that relate our forces that we're going to want to find. Oops. Okay, so we can also look at a structure and imagine a virtual displacement. For instance, in this picture, we have sort of a truss-like picture. And we're going to imagine we have some sort of virtual rotation around the joints at A and D, so that you can see in this picture everything is kind of going off to a corner. And you can also see that the distances that the joints have moved, because we're going to be looking at the force, the work done by the external 4 kilonewton force, and also by this tension in this particular member, TBD. So, to find the work done with that virtual rotation, we have TBD times the cosine of theta, and then the displacement is 1.4 times delta alpha. And then also we have the 4 kilonewton force times the 1.4 delta alpha. And that all was the virtual work done by those 2 forces. We can see that delta alpha can be factored out. We get TBD times 1.4 times cosine of theta plus 4 times 1.4. And so our relationship here is TBD times 1.4 cosine of theta plus 4 times 1.4 equals 0. Now we can factor out the 1.4s in both terms, and notice this allows us to solve for TBD, and we could find it, but we need to know what theta is. So we're going to go back and we're going to look at our picture. This was our theta, and we notice that the tangent of theta is given by 1.4 over 1. So theta is 54.5 degrees. And so from that, we can find the tension in that member, and notice that it's going to be minus 6.88 kilonewtons. All right, so we have one more thing I want to show you. Oops, I had a lot more to work with than I realized there. So here is an example of a linkage, and we want to sort of figure out with some virtual displacement how big that force F is going to be. And the thing that's tricky about this is in this particular type of problem, if you think about it, when we have a displacement, and so sorry that I'm not a good drawer, but I'm doing my best. If we sort of imagine that force pushing down and sort of rotating that particular member a different way, we notice that this member is going to undergo a linear displacement. So we're going to have two sort of virtual displacements that would happen at the same time. We have delta alpha and we have delta x. And we're going to want to know how these are related to each other. And so this problem becomes maybe a little bit more involved than we might have anticipated. In order to do this problem, we're going to call the length of this piece, we're going to call it L, and I'm going to call the length of this piece right here, I'm going to call L2. All right, so let's go to this page. So I have a little more work to do. So if I imagine the work, how much work was going to be done. There's only two forces here that do work, the 2 kilonewton force here and this force here. The 2 kilonewton force, of course, is opposite the sense of my displacement in the x direction, so that's a negative amount of work. And then the force, when we want to think about this kind of going like this, the displacement here is going to be L times delta alpha. And we're going to want to sort of, if this is our angle alpha, we want to look at the force that's like in this direction. Sorry, force parallel. And that is going to be given by F cosine of alpha times delta alpha. And so that is the expression for the work done by the virtual displacement. But the problem is we want to know how are these related. So in order to do that, we're going to use the law of cosines. We're going to be sort of clever here. So in the law of cosines, we can make a relationship between the three sides of a triangle and an angle. We're going to let this be one of the sides. Remember I had labeled this one was L2 and this was L. and we're going to call this one x. So, and we're going to use the two sides that are bordering the angle alpha. And so L squared plus x squared minus 2lx cosine of alpha is equal to L2 squared. So that's using the law of cosines for the triangle. And I can put everything else on one side. And now what I'm going to do is I'm going to take the differential of this equation, which really is like taking the derivative of it. So when I do that, of course, the L's, the length of in the linkage, the L and the L2 are like constants, and so when I'm taking the differential, taking the derivative, I don't get anything for those. Those are 0. Sorry, I made a mistake there with the sign. So the first thing is the x, I get 2x delta x. And then for the next term, I'm going to have to use the product rule. So I'm going to get minus 2L cosine of alpha delta x minus 2Lx sine of alpha delta alpha, but it should have been negative sign, so I changed that to a positive there, okay? Equals 0. So what I can do now is I'm going to take delta x and factor it out of these two terms. I get 2x minus 2L cosine of alpha plus delta alpha 2Lx sine of alpha equals 0. And what this does, and then I can get a relationship between the two. And when I look at this, so this is a relationship between delta x and delta alpha. And just to look at it here, you might notice this negative sign and kind of wonder what that's all about. Let's think about that. If we do think about that, the reason is because if you get an increase in delta x when delta alpha actually is negative. And so that's why there's that negative sign there, because as my angle goes down, my delta x is increasing. And so I'm going to just rewrite this on this page. And we're going to assume that delta alpha is less than 0. And so if we assume that, what we can do is we can get rid of the negative sign. And I'm going to get rid of the factor of 2 as well. And remember, we had our delta u was equal to f cosine L delta alpha minus 2 delta x equals 0. That was my work. I'm going to take all this and I'm going to put it in there, substitute, because that allows us then to simplify. And when we do that, when we do that substitution, we are able then to solve for f, and we get 2 over L cosine of alpha times, delta x over delta alpha. It's easier to do it then. And we get 2L cosine alpha, xL sine alpha, x minus L cosine alpha. And we can sort of figure some stuff out. This is alpha. This is 45 degrees. Our L right here is 200 times the square root of 2 because it's a 45-45 triangle. And this is our X, which is 600. And if we put all those and substitute those in, we find that F is 3 kilonewtons. So, kind of crazy, but that is how we can use this idea of virtual work. So, now that we did that, tomorrow, of course, we'll be looking at homework, and we'll try to finish up this chapter with you looking at the potential energy applications.